building with these silicate tetrahedra, we're going to combine them together in quartz by simply linking the oxygens from one tetrahedra to the oxygens of an adjacent tetrahedra. So one tetrahedra here is linked to this tetrahedra, it's linked to this tetrahedra, and so on, forever and ever in 3 dimensions. Quartz is a silicate polymorph. There are a number of minerals that have this same formula, SiO2. Quartz is one of them. These tetrahedra are the basic building blocks of all silicate minerals. About 95% of the Earth's minerals are silicates. That would be something good to know. 95% of Earth's minerals are silicates. We can further subdivide these silicate minerals based on how the tetrahedra are linked together. We have isolated silica tetrahedra, single chain links of tetrahedra, double chain linked tetrahedra, sheet linked tetrahedra, framework tetrahedra. Now, starting out with the isolated tetrahedra, we have the mineral olivine. So the basic formula for quartz is SiO2. Here we have substitution of magnesium and iron, as well as the basic silica tetrahedra here. So the SiO4 is present here. It's going to link to other SiO4s with the bridge provided by magnesium and or iron. So isolated tetrahedra join in a very simple way. The cleavage plane, a number of cleavage directions, is limited to 1, and we'll talk about what that means in a few moments. Pyroxene is a slightly more complicated type of arrangement of silica tetrahedra. In this case, we have an SiO3 tetrahedra, which is joined to other tetrahedra by magnesium and iron. The result is we have a single chain of tetrahedra that extend infinitely in each direction, potentially. This results in 2 planes of cleavage at 90-degree angles. Amphibole, the next most complicated form of silica tetrahedra arrangement, you can see is a bit more complicated formulaically, and it's a bit more complicated structurally. Now we have 1 chain of tetrahedra linked directly to another chain of tetrahedra in this double chain. This results in 2 planes of cleavage at 60 degrees and 120-degree angles. Common example here would be olivine or peridote. In pyroxenes, enstatite would be a good example of a pyroxene. As far as amphiboles are concerned, the mineral hornblende would be a good example. Increasing the complexity of the organization of these tetrahedra, we go into the micas, also known as the phyllosilicates. Phylos means leaf in Greek. So phyllosilicates are leaf silicates. You'll see why in a minute. Common examples are muscovite and biotite. Muscovite is a clear or yellowish mica. Biotite is black, unless it's very thin, and at that point you can see through it. So here we have sheets of silica tetrahedra joined together. So we have a group of tetrahedra here, joined to this group of tetrahedra here, joined to this group here, joined in here, and so on in 3 dimensions. And the result is we have an excellent cleavage plane, but only one, that splits these into very thin sheets. You can do this with your fingernail, you can do it with a pocket knife, a paper clip, and all kinds of things. You can rip this mineral apart into very thin sheets or plates. And then we have the tectosilicates, such as feldspars, which are 3-dimensional framework silicates. Feldspar means field crystal in German, so that's where this comes from. These are very, very, very common minerals. In this case, they range from a potassium-dominated feldspar here to a plagioclase feldspar, which is generally dominated by calcium, making it dark or black even, or sodium, which results in a white crystal. So the black version of plagioclase would be an orthosite, and the white version of plagioclase feldspar, the sodium-rich version, would be the mineral albite. And just a slightly different way of looking at them here, we have an ideal formula, mineral names out here, Those are missing, so we'll fill it in. Olivine, enstatite, amphiboles, phyllosilicates, tectosilicates, and then pure quartz. These are going to, again, form single tetrahedra, single chains of tetrahedra, double chains of tetrahedra, sheets of tetrahedra, or three-dimensional networks or frameworks of tetrahedra. So this would be like a skyscraper. This would be like sheets of plywood. I don't know how to explain what this would be like other than double chain, single chain, or single tetrahedra. In the case of isolated tetrahedra, these are going to be linked by the bonding of each oxygen ion of the tetrahedra to a cation. These cations in turn bond to the oxygen ions of other tetrahedra, isolating the tetrahedra from one another by cations on all sides. And again, our example would be olivine, iso or island silicate. Single chain structures, again, are formed by the sharing of oxygen ions. Two oxygen ions of each silicate tetrahedra are bound to adjacent tetrahedra in an open-ended chain. These single chains are linked to other single chains by cations. Again, our example would be enstatite, which is a pyroxene, pictured here. It can be kind of a rough-looking mineral, or if you find a nice clean version, you can polish it and facet it and even make an enstatite gemstone out of it. Double chain structures like those exhibited in amphiboles are two single chains that combine to form a double chain linked to each other by shared oxygen ions. Adjacent double chains are linked by cations to form the structure of the amphibole group. And again, our example is hornblende, a very common amphibole. It can be seen like this in fine mineral quality form, or more commonly as this type of mineral, usually fairly fine grained, looks like salt and pepper rock. Sheet structures. Each tetrahedra shares 3 of its oxygen ions with adjacent tetrahedra to build stacked sheets of tetrahedra. Cations may be interlayered with the tetrahedral sheets. Micas and clays are the most abundant sheet silicates, and because they're sheet silicates, they can also be known as phyllosilicates, which means leaf or sheet. Again, muscovite is a common sheet silicate, as is the clay kaolinite. Feldspars generally break down chemically into other minerals. A lot of the cations go away, and what's left behind becomes a clay. Kaolinite is a very common clay that you'll find in things like candy bars and ice cream and basically anything that you want to add weight to, but no flavor. So it's tasteless and generally harmless. Coffee whitener powder that, you wonder, what is this stuff? Well, it's mostly clay. So you can ask for more clay for your coffee. These phyllosilicates turn out to be very important. Clay has many, many uses. We're not going to go into those in this course, but take my word for it, it's a big business. So these feldspars, the white colored material here, would be the mineral albite. This is going to break down chemically to become the clay kaolinite. Tectosilicates, also known as framework silicates, are three-dimensional frameworks where each tetrahedra shares all of its oxygen ions with other tetrahedra. The most abundant framework silicates, and therefore the most abundant minerals in the Earth's crust, are feldspars. Another very common framework mineral is the mineral quartz. These silicates can be very simple with only silicon and oxygen, or they can contain varying amounts of sodium, calcium, potassium, magnesium, iron, titanium, etc. This would be the mineral quartz. You can see the tetrahedra with the silicon here, 4 oxygens around each one, linked to tetrahedra with 4 oxygens, so on in every direction. Common examples would be the mineral quartz here. This is a clear, prismatic, terminated series of quartz crystals. This is also quartz, but it's got a different color. We talked about this before. The honey badgers ran wild through these crystal lattices, allowing iron 3 instead of iron 2 to substitute for the silicon. And the result is this purplish tinge that gives it the variety name amethyst. So it's an amethyst variety of quartz. In every technical aspect, This is quartz. This is quartz. What we call this rock crystal, and this is called amethyst. Carbonates contain the carbonate ion CO3 2- as the basic building block. The carbonate ion consists of a carbon surrounded by and covalently bonded to 3 oxygen ions in a triangular relationship. Groups of these triangles are layered like sheets bound together by layers of cations. In the case of calcite, the cations are calcium 2+. Oxides are minerals in which oxygen atoms are bonded to cations, usually metallic ions like iron 2+ and iron 3+. Most oxides are ionically bonded. Oxides are very important as a source of metals, and in the case of iron, the mineral hematite is a primary source. This mineral hematite, iron oxide, has the exact same formula as common rust, although common rust may contain some water as well. Sulfides are made of the basic building block, sulfur 2- bonded to metallic cations. Most of these minerals are opaque. You can't see through them no matter how thin you slice them, and they look like metal. A good example is pyrite. It looks like gold. Now, if you're a geologist, you would say it looks like pyrite. But if you are an old-timey prospector pounding on rocks in the American West 150 years ago, you'd say, I'm rich. All my troubles are over. And then it turns out to be fool's gold. Sulfates consist of sulfate ions, SO4 2-, which is made of a sulfur ion surrounded by a tetrahedra of 4 oxygen ions. As I mentioned a minute ago, gypsum is a common example. Gypsum is calcium sulfate with water, making it part of its lattice. Anhydrite is CaSO4 without the water. And that makes sense. Anhydrite means without water. And the difference in use is we use gypsum to make drywall, which forms most of the walls that we see in houses, apartments, office buildings, etc. It's cheap, it's basically fireproof, and cheap, easy to get. So a thought question for the chapter. Which physical properties of sheet silicates are related to their crystal structure? That should be a pretty easy one. Take a look at what a silicate looks like, and as we go into cleavage in a few minutes, you should be able to answer that question. Physical properties of minerals are important to us for the identification of minerals in what's known as a hand specimen. Essentially, it is just what it means, or sounds like. I'm going to hand you a mineral and you're going to tell me what it is. Under non-COVID rules, that could happen. Under COVID rules, I'll just talk about it. Hardness refers to resistance to scratching relative to Mohs scale of hardness. Mohs scale of hardness is a scale of hardness developed by a guy named Moh. Now, he picked 10 fairly common minerals that have 10 very different hardnesses. This ranges from 1, the mineral talc, to 10, the mineral diamond. Talc is very soft. We make talcum powder out of talc. With a hardness of 1, you can easily scratch it with your fingernail. Diamond, on the other hand, has a hardness of 10. It will scratch every other mineral that is naturally occurring on or near the Earth's surface. Cleavage is a tendency of a crystal to split along planar surfaces. These are planes of weakness. Cleavage is defined as perfect, excellent, good, fair, poor, and none. Perfect cleavage means you'll get a nice, clean, flat surface. Excellent is a pretty nice, clean, flat surface. And none means that the mineral will break like you, say, hitting a brick with a hammer. It's very irregular, no flat, shiny surfaces at all. So perfect cleavage. Easy cleavage with extremely smooth surfaces. Muscovite is a good example. Good cleavage. This is what you would observe in an amphibole and a pyroxene, like hornblende and enstatite. They're going to cleave easily, but they can also be broken. Fair cleavage. This is observed in ring silicates like the mineral beryl. Beryl is also known as... Beryl is going to display irregular cleavage from breakage along non-cleavage surfaces. It can be used to help identify a mineral, such as quartz, which has a very poor cleavage, and calcite, which has excellent cleavage. A fracture is the tendency of a mineral to break along irregular surfaces other than cleavage planes. The shape and texture of the surface determine the type of fracture. Examples of fracture types include fibrous, splintery, conchoidal, and a few others. So fibrous, the mineral breaks apart into fibers. Splintery fracture, seems like the mineral would break into splinters. Conchoidal might be one that you don't recognize. Conchoidal means shell-like, as in a seashell, as in a clamshell. So when you break quartz, which has conchoidal fracture, you'll see these little clamshell-like features appear on the broken surface. So here we have some examples. Cleavage in one direction, muscovite. This peels away in thin sheets. In feldspars, we have cleavage in two directions, our example being, say, albite or anorthosite. Cleavage in three directions, in this case cubic cleavage, is exemplified by the mineral halite. Cleavage in two directions, in this case rhombohedral cleavage, because the resulting surfaces are rhombohedral shaped, is represented by the mineral calcite. And here we have some examples of fracture. Starting with the upper left, we have quartz exhibiting that seashell-like fracture that we talked about a few minutes ago. The fibrous fracture of asbestos. Here we have the Hackley fracture of metallic native element, and earthy fracture. This would be similar again to breaking a brick or smashing some pottery. I'm not encouraging that. If it happens accidentally, it would look something like this. Now, the way a mineral reflects light is also going to be diagnostic. This is the luster. Luster is the way a mineral reflects light. It's going to be determined by the kinds of atoms present and their bonding, which in turn determine the way light passes through or is reflected by the mineral. In the case of metallic luster, the mineral is going to look like a metal. This is going to be opaque. Resinous luster looks like resin. Here we have an example of amber, which is fossilized tree sap. So this resinous luster allows us to see into the amber. Lastly, here we have vitreous, which means glass, therefore glassy luster. And the example is a rock crystal or quartz. Now, other things are called rock crystal too, so beware. That's not a real geological term, but you'll see it very, very often, particularly at rock shops and all kinds of stores that sell junk. Okay, color is a tough one. Color is imparted by light, either transmitted through or reflected by crystals or irregular masses of the mineral. It's not particularly useful for identifying a mineral. Calcite, for example, can be any color you can imagine, and it can exhibit 300 or more crystal forms. We often have to determine the mineral name by bulk chemistry rather than color. An example of minerals that are characteristic colors would be emerald and sapphire. Sapphires are blue because of iron and titanium. Emeralds are green because of the presence of chromium. Now, one thing that is very useful for identifying some minerals is the color of the powder of the mineral. Streak. Color of a powdered mineral, usually on a streak plate. This is unglazed porcelain. It's hard but not incredibly hard. If you drag a mineral like pyrite across the surface of a streak plate, you'll get a color, in the case of pyrite, of dark green, even though the mineral looks like gold.